Alright, geometry, this is your lesson 821 notes. So 821 is all about ratios of similarity. And so just a reminder from similarity, this picture is actually a little bit like a dilation. Like if we're dilating all of these, I don't know what these are, like storage sheds or houses right here, from that point of dilation over here somewhere. So they're getting larger and larger. So what we could do to find like the scale factor, or sometimes called the zoom factor, is dividing one of the bases of the house by one of the other bases. Okay, and so like let's say that this house has a base of, and if we were using a ruler, let's say it was like 6 centimeters, whereas over here maybe that house has a base of 3 centimeters. So we'd find that scale factor just by dividing those base measurements. 6 divided by 3 is 2. So it's dilating by a scale factor of 2. So we're just multiplying by 2 to get the new base. All right, so that's a little bit of review from what we did last semester. So let's go ahead and get started. All right. So number 67 is talking about a Mighty Mascot, their school's flag or banner, and they want to design a flag, and so they created a scaled down version of the flag that they would like. So they said that their flag is 1 foot wide and 1.5 feet tall. So I went ahead and put those measurements on there on Archie's version. And the student body thinks that the final flag should be 3 feet tall. So I already kind of made a measurement. We want this larger flag to be 3 feet tall. How wide would this enlarged flag be? Okay, so we have to ask ourselves, how many times does 1.5 go into 3? Okay, and so if you said 2 times, that would be right. It's 1.5 plus 1.5 equals 3. All right, so since that small height goes into the big height 2 times, that means that this width is going to be 2 times larger. So then what is 1 times 2? That's right, it would be 2 feet tall. Or sorry, not 2 feet tall, 2 feet wide. All right, so how wide would this enlarged flag be? It would be 2 feet wide. All right, moving on to this next question. If Archie used $2 worth of cloth to create his scale model, then how much will the cloth cost for the full-size flag? Discuss this with your team. Explain your reasoning. All right, so what I did, it says to obtain the resource page and scissors and cut out the copies that we have. So if you're like me, my printer doesn't really work that well. I didn't really want to print these off, so I'm going to show you a way to figure this out without needing to actually cut and paste anything on here. So we know that the small flag is 1 by 1.5. We know the bigger flag we want to be 2 times bigger, so that would be 2 by 3. That means that we can fit 2 flags wide and 2 flags tall. All right, so I sectioned this off using that knowledge. So we know that one of these flags we can put here. We can also put another one over here. And then we could also fit one if we flipped it upside down right here. So this would be 1, 2, 3, and 4 flags are going to fit in there. All right, so if we know that each of these flags is $2, then we should be able to figure out how much that big flag would cost. So we want to multiply $2 times how many small flags would fit into the big flag. So 4 small flags fit into that big flag, so we're going to multiply 4 times the $2. And so that 2 times larger flag would cost $8. Okay, so we're not just going to multiply $2 times 2, even though it is 2 times the width and 2 times the height, the area is actually 4 times larger. All right, and then we're going to use that same reasoning to figure out how much it's going to cost for a flag if we want it 3 times as wide or if we want it 4 times as wide. All right, and so I already kind of have it sectioned off here. 3 times as wide, we can section it off into sections of 3 on the top, and then if it's 3 times wider, it's also going to be 3 times taller, so we can section it off into thirds here on the side as well. All right, and then we can fit our flags here. I started by just kind of making this first flag here. I know that it's going to come to a point here and here. And then we could fit in a couple more flags if we rotate those around. And so instead of getting the paper and actually cutting all that stuff out, I can visualize that within the flag. So again, the second section right here, I can fit 2 flags right here, since this is a 1 and this is 1 inch wide, and then I can fit another flag if I flip it upside down. And then same with this section, I can only fit 1 flag in there. So overall we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 9 small flags fit into that big flag. So if it's 3 times as wide, it's actually 9 times the area. The area is 9 times bigger. So we're going to multiply those 9 flags times $2 since each of them costs $2. And so the cost of this flag would be $18. And then same thing over here, I went ahead and sectioned this off. If it's 4 times as wide, that means we can fit 4 flags up here, right here across, and then we can fit 4 flags down 4 times as tall as well. So again, this bottom spot, only 1 flag can fit there. In this top spot, we could fit 1, 2, 3, 4, 5, 6, 7. This other spot, we can only fit 3 wide, so then 1, 2, 3, 4, 5 right there. And the third level, we can only fit 2 flags wide, so there's 1, 2, 3 flags that we could fit into that area. All right, so the total number of flags that we have here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So when we make it 4 times as wide, it's actually, the area becomes 16 times larger. So that's what we're trying to notice, is that pattern between the scale factor, the side, and the area scale factor. So we're going to multiply 16. There's 16 small flags that fit in that big flag, and each of those small flags cost $2. So the total cost of making that flag 4 times as wide would be $32. All right, so the pattern of observation of those flags, we are going to use that to predict if we have an area that is 100 times larger than the area of our small shape, or small or similar shape. All right, so when the width, write this down in our notes, when the width was enlarged 2 times, then the area was enlarged by 4 times. Okay, so that was from our first example. Whenever the width was 2 times larger, we could fit 4 flags in there. All right, so then I'm not going to write all this out again. When the width was enlarged by 3 times, then the area was enlarged by 9 times. So that was the second example of those flags. When we multiplied the width by 3, we actually multiplied the area by 9. All right, and the last flag that we did, the width was 4 times bigger. Then the area was enlarged by 16 times. So as our last example, when we had a width that was 14 times bigger, we could fit 16 triangles in there. All right, so hopefully you're seeing a pattern. How do we get 2 to equal 4, 3 to equal 9, 4 to equal 16? 2 squared is 4, 3 squared equals 9, 4 squared equals 16. So what we're doing is, if we know the scale factor, the linear scale factor, then we know how to find the area of the new shape. We just square that scale factor. All right, so if we know that the area of one of our shapes is 100 times larger than the area of a similar shape. So that's going backwards. We know that the area is 100 times larger. Then we need to figure out what was the width enlarged by. Okay, so what squared equals 100? Hopefully you know this. 10 squared equals 100. So we would multiply the ratio is what we multiply by. The ratio would be 10 for the corresponding sides, or for like widths. All right, so if we know that the linear scale factor is r, so any number r, then we know that the area is r squared times larger than the smaller shape. Okay. So if we know the linear scale factor is r, then we know that the area scale factor is r squared. And so we just have a couple of example problems to do together. Number 8-69, and then we will be done with these notes. So we know that At the right, that right shape has an area, or sorry, this left shape has an area of 17 millimeters squared. If she enlarges this shape with a linear scale factor or zoom factor of 5, what will the area be of the enlargement? Okay, so if we know that the linear scale factors, now that's r equals 5, then we know that to find the area scale factor, we just square that number. So 5 squared is 25. So the area of this shape is 25 times larger. So we're just going to take the original 17 and multiply it times 25. And that is going to be the new area, which is 425 millimeters squared. In part B, we have the area given for 1, and then we have both of the sides given. So since we have both sides given, we're going to use that. When we are given the sides, that gives us the linear scale factor because they are just lines. So the bases are 40 and 10. So to find the linear scale factor, we just divide those two numbers. So 40 divided by 10 is 4. All right, so the right-hand side, that larger shape is 4 times larger than the smaller shape, which means that the areas, let's see, so that answers our first question. What is the linear scale factor? And then to find the area of the smaller figure, we have to figure out what the area scale factor is. So we just square that. 4 squared is 16. So that is not the area of our shape, but that's how we can find the area. So we multiply whatever the small area is by 16 to get the larger area. Or if we go backwards, we can divide. So we're going to take the area of the big shape, which is 656. We're going backwards, so we're dividing that by 16 to get a smaller area. If we multiplied, we get a bigger area. All right, so 656 divided by 16, I get 41 units squared for that smaller shape. All right, guys, there is just one practice problem from this lesson. So I want you guys to do that, and there's no exit ticket for this lesson. So make sure that you have the notes. If you have questions, mark it on your notes so that I can answer those on Tuesday. All right, thank you guys for listening.